All right, everybody. Thank you for making it today. It's good to see you. It's a beautiful day outside. Amir, you're shaking your head. No?
It's hot.
It's hot. Oh, it's too hot?
Yeah. Almost 90 today.
Is it 90?
It's 88.
Okay, never mind. It is hot. It's hotter. I've been inside a lot, so I didn't notice.
There's also a lot of pollen. The air quality's really bad today.
Okay. Well, I'm sorry.
If you want to see me running in and out, just going to the bathroom to blow my nose because that pollen got to me.
Well, that's quite a bit of information, and thank you. Um, okay, so today we're on session 22. Failure criteria 1. Okay, and the videos are broken into 3 parts again, with the first part kind of going back and talking about how we characterize materials, the tensile test being our primary mode, and then session 2 gets into maximum normal stress theory for brittle materials, and part 3 of session 22 then goes into maximum shear stress for ductile materials. Okay, so I'll just kind of give, I know you're doing various things, but just give kind of a couple of thoughts on the maximum normal stress theory and the maximum shear stress theory. Okay, so for maximum normal stress theory, okay, there are kind of a couple ways to approach this. One is through Moore's circle, and the other is through what are called sigma 1, sigma 2 plots. Okay, and it takes a little while to get comfortable going between the two. Okay, so we typically start kind of with the base case of uniaxial loading, okay, and then we build from there for other more complex cases. All right, but here are the rules. Okay, so this is first of all, do not apply it to ductile materials. Rule number 1. Okay, this one is for brittle materials, and we've talked about brittle and ductile in the past, right? But brittle materials are those that kind of have a catastrophic or very sharp break. They don't have necking. They typically don't have a large modulus of toughness. They have a break plane that is orthogonal to the normal stress. Okay, because the normal stress is kind of the trigger. That's what causes it to fail. Okay. So first, yes, use it on brittle materials. Okay, and then if sigma 1 and sigma 2 are both greater than 0, or sigma 1 and sigma 2 are both less than 0, then we can use the relationship that sigma 1, okay, needs to be less than or equal to, or in the notes, I think we even say equal, all right, but needs to be less than or equal to the ultimate tensile strength or ultimate compressive strength. In this case, we're saying that they're the same, or the absolute value of sigma 2 has to be less than the ultimate tensile or compressive strength, which we're considering the same. And if sigma 1 and sigma 2 do not share the same sign, then we have to look at the absolute value of the difference of them and make sure that is less than the ultimate strength. Okay. Those are the rules. What does it look like on a Moore circle? Well, on a Moore circle, what you have for the first case, where you have sigma 1 and sigma 2 on the same side of the tau axis. Okay, so if they're right here and here, okay, then what we're looking for, right? So this could be sigma 1, this could be sigma 2, okay? So you go ahead and you're like, okay, I'm going to draw my Mohr circle like that, okay? But you also have a sigma 3, right? And so what you end up looking at okay, actually it doesn't matter, sorry. You're just looking, you just got to pick the maximum normal one. That's the whole idea, all right? You just got to pick the biggest one. Okay? Or, I mean, you can draw it, it's okay, right? But either way, it's the biggest, right? It doesn't really matter. This is the radius of this circle is sigma 1 over 2. Okay, so that is one case. The next case is where you have them on this side. And once again, this could be called sigma 2, right? We said typically sigma 1's the bigger one, all right? So if you wanted to call sigma 1 because it's more negative, the more problematic one, that would be okay, all right? But again, we're looking at the largest one, right? And the biggest one here, or the one with the largest magnitude, right, needs to be less than the ultimate tensor. If you have one here, right, then yes, we start to look at the difference, okay, between these two. Hold on. Yeah, let me make sure. Yes. No. I did. What am I doing? Yeah. Okay. Sorry, guys. That's it. You don't have to do this. Yeah, that's why I was confused. It's not this. It doesn't matter. This is for maximum shear stress theory. Sorry about that. Okay. So so either way, you're still looking at sigma 1, sigma 2. You just pick the max. Okay. And when you plot this on what's called a sigma 1, sigma 2 plot, plot so many more circles, okay, like this, what you end up wanting to be is in the box, okay? And this corner right here is sigma ultimate, sigma ultimate. This corner right here is negative ultimate, negative sigma ultimate, okay? And you want to be in the box. So in the box, we do not have failure. Outside the box, you have failure. Okay, so right, you can make some kind of bad joke about being penalized for thinking outside the box, right, Apu? Okay. The other theory is the maximum shear stress theory. Okay. And this one is for ductile materials. Okay. And in this case, what we're looking at is the shear stress, okay, being less than a maximum threshold. Okay, so for this, okay, what we're saying is what I got confused about. All right, you don't need any of this for this. This is all good. Okay. I apologize. I wasn't using notes and I was just going off my head, and that's what happens. So for ductile materials, this case, we do have the condition where if sigma 1 and sigma 2 have the same sign, okay, then we say it's less than the yield strength. And if sigma 1 and sigma 2 have opposite signs, then we have the difference needing to be less than sigma y. All right. Now it's a little weird to have it written out like this because you're saying, oh, you're talking about maximum shear stress. There are no shear stresses in what we've written so far. Okay. Well, these criteria come from Mohr circle. They come from kind of what we've learned already. So if we look at a couple different cases here, okay, let's say we're both on this side, okay. In that case, the maximum shear stress is R, right? R is equal to tau max. Okay, and what we're saying is we want to be less than that. In the case if they're on this side, okay, same deal. Okay, they're both negative. R is equal to tau max. And if this was sigma 1 and this was sigma 2, right, what we're saying is that sigma 1 divided by 2 has to be less than or equal to tau max. Okay, and over here, we're saying that sigma 2, absolute value, right, has to be less than or equal to tau max. And then in this case, when they're on opposite sides, then we know that, well, it doesn't have to be, the center doesn't have to be there, but that the tau max needs to be greater than the difference between sigma 1 and sigma 2, like that. Okay, so in all cases we're interested in tau max, but it's indirectly expressed in these expressions that we see here. And why is that? Well, that's because sigma y has a special relationship to tau max, all right? So in this case, if I have a uniaxial load, right, I have one principal stress out here, and I have zeros for sigma 2 and sigma 3. And we can say that tau max is just equal to sigma 1 over 2. Yes?
Like the last slide you were on?
Yeah.
Was it supposed to be like sigma 2 over 2? Tau max 1?
Oh, good question. Yes. Yes. Okay. Thank you. Tyler. Got it. Okay. So essentially wherever you see tau max, or wherever you see sigma y, right, this is the same thing as a tau max. Well, this is the same thing as 2 times tau max. Okay. And in the video, I go through a few more details here. One of the fascinating things about these theories is that they actually do tell you how the failure is going to happen. Okay, just physically. So let's take off our analytical, well, we're still being analytical. Let's take off our kind of quantitative hats. Maximum shear stress theory is saying that it's the shear stress that causes failure. Okay, which means if it's shear stress, it's along the lines that you could find, okay, when you look at the shear stress. And if you have axial loading, right, you know you got to go 90 degrees on Mohr's circle or 45 degrees on the actual element, okay? So we go 45, right? So in this case, we have an element that's being loaded like this, right? We have to go, okay? So if this was sigma x, this is sigma y, or this is, it's 0, but we'll just call this the y direction. Okay. We have to rotate, well, we can rotate either counterclockwise or counterclockwise, or say, what did I say? Counterclockwise or clockwise, right? So in this case, if I'm here, which is I am here, right, and here, I'm going to go clockwise 45 degrees or 90 degrees on Mohr's circle. Okay. So what does that mean? That means that this element, okay, that's gone 45 degrees, now I have this face, which has become my sigma x, or this has become my x prime. This is now my y prime, okay, because that's the clockwise 45 degrees. And I have an average stress, or I have right. This is, I'm down at this point, right, so that my my stress, okay, is going to be coming out like this. Oh, I should use a different color. Like this. That's the new sigma x prime. This is the new sigma y prime. This is the new sigma y prime, right, as well. And I have shear stress, okay, and it's positive like this, okay. And the failure happens along this, is because of this shear stress, okay? So it's going to happen along this direction. That's where failure or fracture line. Okay, and the classic example that people share Okay. Take one and pass it around. Okay, this is our feel good. There's some over here too. Take one. All right. So this is the classic example. First question is, oh, I'm so tired. Okay. Yes, the fracture is on this line, and it's not along it, it's normal to it. This is for a ductile material. Oh my goodness. It's normal. I'm sorry, guys. Okay. What are you holding in your hand? Are you holding a ductile material in your hand? No. Okay. So we're using the maximum normal stress theory. Okay. All right. Now, how can fracture happen normally if I put this under torsion? Okay, well, it will snap, right? So let's say this is under torsion, right? And this is in the video too. It's better in the, I'm doing, the video is better than I am live. Okay, I'm sorry. I didn't get much sleep last night because I was doing this. Okay, so if I have, this is under torsion, okay, and I have an element there, right, and this is X, okay, this element is going to be, and I say this is X still, this element is going to be experiencing shear stresses like those, okay, does that make sense? Because I have shear stress here, 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 here on the element. Okay, so there's the shear stress. If I call this Y, okay, like that, and I flip this over, right, I get an easier thing that I'm more comfortable with dealing with, where X is coming out the right and Y still at the top. Okay, and this is a positive. Okay. So, is there any normal stress in this case? Well, in this orientation, no, there's not, right? So, the question is, if this is maximum normal stress theory, what in the world are we talking about? Well, we can find a state where we rotate it 45 degrees, right? Where we get principal stresses. And we will get principal stresses where it's like that for a particular orientation. Okay. So now this will fracture along or orthogonal to that plane, okay? So if I take a piece of chalk and I twist it under torsion, I'm not going to get a clean break. I'm going to get breaks at 40, I'm going to get a break at 45, or I'm going to get a pretty clean break. It's going to be at 45 degrees. Okay, so everyone take your piece of chalk, all right, and just twist it. Twist it, and then look at the angle. You're not, you can do it. You can do it. There you go. Yes, you can do it. I know you can do this. All right. Now, besides making a mess, what do you see? You see fractures. That's, wow, Sudeep, yours is good. Yeah, and so is yours. I mean, wow, yours is good too. Okay, some of you are better at pure torsion than others. Is there any more chalk for Matt? Okay, yeah. Kelly. Oh, you have chalk? All right, you got it? Okay. So what you see here, right, is that under pure shear, okay, the normal planes are at 45 degrees, okay, to the shear stresses. And so we break on the normal planes, okay, which are described by pure shear. Now, what happens if you take another piece of your chalk? It's still brittle material. It's still supposed to fail under normal stress. And I bend it. What do you think is going to happen? Pop. Okay. Now, and which side? Okay, so I didn't tell you this. Right. Well, if I bend it down this way, right, the top is going to be under tension or compression. If I bend it this way, I put a negative bending moment on it. Tension, right? And the bottom is going to be under compression. Okay. Right now, we're just using the maximum normal stress theory. Okay. And next time we meet, we'll talk about another theory for brittle materials that takes into account the fact that for brittle materials, they're weaker in tension than they are in compression. Okay. So typically, a brittle material actually will fail first in tension and second in compression. Now, So if you break this, I don't think we can really see it, to be honest, because these cracks propagate so fast. But what you would expect to see is that if I put a bending moment this way, it's going to cause there to be tension on the top and compression on the bottom. Okay, and it would fail first under tension because it has less strength there. Okay, or it has less strength under tension, and it's at the top. Okay, so let's see. Let's see, and then, right, we're applying normal stresses, okay, and they're bending. So we expect more or less, okay, more or less it to be 90 degrees to this plane. It's not going to be as nice as what we just did with pure shear. Why? Because the bending stresses are not uniform, right? They don't go uniformly, right? They go to 0 at the middle. So the middle is at the neutral axis. It has no bending stress. All right, well, let's see. I don't know exactly what's going to happen, but I have an idea. All right, I was going to do this before. So if I do this, woo! That is pretty sweet. That's better than I thought it was going to be. Right? That is a normal crack, fracture, right? Did anyone else do it with the remains? You don't have enough? Yeah, you got it. Yeah. You got it. Okay. All right. Okay, so these are for brittle materials. I'm sorry, I'm very tired. Okay. I don't have any ductile materials with me. Oh, actually, I probably do. I mean, I have a ton, but I'm wearing some ductile materials. I have leather on my shoes, right? I'm not going to tear those apart, though, for you. Okay, nor do I have the strength, okay, to do so. Actually, I haven't thought about this much. We're just musing here, and I'm taking you away from your problem solving. But paper is kind of a ductile material, right? Okay. And how do we see paper failing? Well, if it's a ductile material, it's going to be failing under shear more than tension, right? So if there's a way to kind of apply a shear, right, to it, it's going to be easier to break. And so, I mean, tearing is kind of that's a little bit different. That's a different type of fracture. It's I can't say that's necessarily shear, but if how could we apply a shear versus? Anyway, we had to think about that. That's a demo that we can think about. Well, this would be normal, right? It's definitely very strong in this direction, right? I need some way to kind of shear it, and I mean, tearing is. It's not exactly shear. It's like, so there's when you study fracture, in DMC, you'll do something, you'll study fracture. There's like mode 1, mode 2, and mode 3. Okay, mode 1 is when you're just kind of like splitting it apart. Okay, mode 2 is more of the tearing, and mode 3 is like tearing. It's like this kind of thing, right? So typically we're tearing more in a mode 2, like when we tear like that. But that's a lot easier, right? Okay, good. Anyway, so we're done musing, and I almost want to delete this video because of all the mistakes I just made, but it's live, we keep it. All right. So go ahead, work on the problems. If you have any questions, I'm happy to answer them. Nice glasses. Thank you. Did you see a movie?
Oh no, these are from physics lecture from like a few weeks back.
Oh.
Feels to see different rays of light.
Oh, you
Test
both?
them out?
Huh?
You want to test them out?
Sure. What am I looking at?
Just look at the corner, you can see rays of light.
Oh, it's like a prism?
Yeah.
Okay. Oh, yeah. That's nice. Wow.
Hey, just throw out the chalk.
You can throw the chalk, or just put the chalk on the chalkboard, right? Chalk on the chalkboard, so someone else might use it. I think that looks really good.
You look pretty snazzy.
Yeah, it looks really good here, don't I? Wow, you all have them?
Oh my god.
Well, okay, well.
Oh no. I woke up very late.
That
You
was
did
fun.
too.
What?
You both, you both came in like 3 minutes of each other.
I know, right?
Oh,
He
I didn't
was,
do that.
he went from like Cook, and then I came from here, so it was actually a miracle that we came here at the same time. Because I thought he was going to be later. He's on Cook. I was like, Cook versus. I just got really lucky.
Well, are they running better now or worse? Because it's really hot. Sometimes when it's really hot, people want to take the bus, right?
Maybe. I mean, it could be also due to the strike as well. Not as many people are going to the
Classes.
Yeah.
Yeah.
Whoa. Oh, you cheater. Cheater. So she like cheater. Cheat. This computer's only human. Ooh. I think this is
Yeah. So now you have a new incentive to go into a classroom and break all the chalk. Don't. But even though it's in the name of engineering, it's probably not very kind.
I think it's a good idea.
You think it's a good idea?
I think it's like a good, unique. We could convey this to our other professors so they can learn too. It's like give back and like they give us knowledge, we give them knowledge too.
Yeah. Well, your other decant engineering professors will be familiar with the trade.
We could impress them. Like, oh,
Yeah.
you know this. Wow, he's so smart. Let's just give him a free A.
That works every time, doesn't it?
Every time.
Yes. Any questions? How's it going, guys? Does problem number 1 look right? I've never used one of those.
I think so.
Number one works fine.
What does it look like?
It's
On yours?
just
Because I did the preview on my end, and I was like, I don't know if this is working or not. What does it look like?
It's the same question. Session 16 question. It's the same.
this gives you another column on the bottom of all the possible things you can
Okay, and you pull them up.
Yeah.
Oh, okay. Good. So that's what I was hoping it would do, but I couldn't actually see it.
Question 16. Yeah.
Be right back. So I went to the vending machine. I thought we could do the same experiment with a ductile material. I don't want to eat this though, so it's a Milky Way. I thought it would be more ductile than the Snickers because the Snickers has the nuts in it, right? Okay, so if I don't think we're gonna be able to see this because I think it's gonna be too subtle for us because it's gonna be like. Okay, so I'm going to try to do it so I don't touch it, so I don't damage it, well, I mean, so that it's still sterile. Okay. So here we go. So the thought is that if we shear this, if we put it under pure shear, it would fail on along the shear, right? And so we won't see the normal, we won't see the 45 degrees. We'll see kind of a cleaner break. I think we're just gonna see a bunch of goo. Okay, that's what I honestly think we're gonna see. All right, but I thought it was worth a shot, and for the name of engineering, $2.25 is a modest amount to pay. All right, so here we go. We're gonna twist. Oh, okay, look, actually, that is not good. I think that's actually kind of brittle. So you see the outside chocolate is actually pretty brittle, right? And so it actually is failing like the other one is. Under the 45 degrees, you can kind of almost see that it's failing in the 45 degrees. Okay, so this experiment didn't go like I wanted. Okay, if we keep going, yeah, the goo inside, yeah, this is impossible. This is impossible. You can't. It looks more like, it looks more like a fluid. It is, it's a combination, it's viscoelastic. So anyway, but you guys want some of this, now you let me. You'll take it? All right, let me split it up. Raise your hand if you want a little bit. Okay. Only a few of you, so here. Oh wait, take that. I think you have to take that, because otherwise it's not sterile for the other people. I had 2 chocolate chip cookies from a seminar this morning, so I'm like, I don't need more.
Thank you.
Well, that's your breakfast?
Yeah.
I had another cookie for breakfast, in fact.
Really?
Yeah,
Oh wow.
it was really bad. It's all for this class, actually. I don't get sleep the night before this class.
Yeah.
But from after this semester, for years to come, unless I get kicked out or the students really, really, really hate it, I have a lot of material already done now. Maybe. Okay, so that was a failed experiment.
Cast iron. I know. But
You're able to do canvas on that thing?
yes. Oh wait, no, not this.
Because that's just paper.
But yeah, just write notes here.
But can it hold internet websites?
No, I can't.
Oh.
You know, I just take notes on this.
Oh, and then you're answering on your
Answer,
phone.
yeah.
Oh, okay, now I got it. It's like,
inside my notes.
Inside your notes.
He has a like a note taking application, and like he can
Oh.
somehow browse the
What is? That's interesting. Note taking application.
so
Like not OneNote, obviously.
No.
yeah, now
But Notability or that's something.
So you can create a web full of notes.
Oh.
And then you just
Which one is this?
Obsidian. So you have to go to your node, whatever you need, click it, go to your notes.
So like a mind map.
Yeah.
Yeah, I use mind maps actually. Not usually with the node. Like, I just make trees. But this way, I guess you can have pretty interconnected.
Yeah, you can, if you need to find one thing, connect to another, and just go through all the notes that you need.
Wow. You've been doing this for a while.
Recently. So I only have last couple weeks of notes.
Yeah. I use mind maps. I was using Free Plane for a little while. Got frustrated that it wasn't the real one. Hello. How are you doing? Hey. Good to see you, Spots. Yeah.
So on the ultimate screen, is that the most stressing or stressing?
So when we talk about ultimate strain, we're talking about brittle materials typically.
Oh, so that.
Well, for this section, but yes, ductile materials can have ultimate strength too. Okay, but ultimate strength for brittle materials is kind of where it just fractures.
So we're seeing
Yeah.
brittle for these questions.
Well, if for the ones where we're using ultimate strength, yeah, those are brittle materials. So we're using a maximum normal stress theory.
Okay.
And but you're right. For ductile material, essentially, yeah, you can begin to have necking somewhere after the ultimate transition.
Also, any questions? We're going to get a reason to respect the question for exam 2.
Probably next. Actually, I'm pretty confident next one.
Thanks.
Yeah. Yes.
He just looked on something that
Still cheating. Yes.
why is it?
So, for this one, remember to give a negative value. Give. Okay, so it's constants. Okay, so you're trying to find shear stress. Yeah, it should just be shear stress, yeah. And it should be the difference of the two. I agree with that. Okay.
This is the same question for session 16.
Yeah.
I plugged it into my Desmos. It gave the answer is incorrect for me.
But I copied it from session 16. Did it not get corrected?
I don't know. So I went back to session 16, plugged it in, gave the same answer, but for 22, it's not marking correct.
Take a look. I thought I copied it from section 16 as well.
Question 3. That's just section 16, question 4. That one.
So that one worked.
Yeah.
Yeah, and that one I had to change. That one's more complicated because you're looking for the absolute maximum shear stress.
You won't have to practice stuff. Yep.
Ah, yeah. So it didn't. Yeah. So it's interesting. Because we fixed it in section 16, right? I had made a boo-boo in section 16, right?
I don't remember.
I think so. And I thought I fixed it. And then, but the fixing, I'm learning, you're teaching me things. The fixing didn't mean that when I copied it over, it was fixed. I think it took the old version. Because this is the new version. I just flipped it around. Oops.
Professor,
Mm-hmm.
I have a question about the formula. So for the second part, I did the same thing, but
Yeah.
I was getting 2/3 instead of 4/3. Where did the 4 come from?
Okay, so this is because. Okay, let me just update this, and then I'll answer the question. Oops, that's not right. I don't know.
No, Jalen took a picture and sent it to you.
Yeah, that's motion.
There's also fire.
Yes. Yes. No pirate. Okay. Seems like yes. We try to find a comfortable position. This is I guess position. Okay.
Yeah, so for that, there were no negative values, right?
No, I don't remember. I supposed to be positive on mine.
Yeah, because that's what I was getting. What did I do wrong?
Well, not-
Something's not right here. Third, I got negative values. Hold on, let me leave it for now. I'm gonna go back into.
No, it is negative.
Yeah. Yeah, they're negative. Okay, good. Yeah. Okay. So. Okay. So now to your question, Shlok. The reason it's 4/3, right, is because it's a cylinder. So when you're doing the transverse shear or the transverse shear stress on a rectangular cross section, you use 3/2 times the average shear stress, and when you're doing it on a circular cross section, it's 4/3 times the average shear stress.
Oh, I was really wrong. I was doing VQ over IT.
Well, you can do VQ over IT, but you should look in the notes because we derived it so that you would never have to do that again if it's a rectangular or a circular cross section and you're on the neutral axis. Okay, because that's where the maximum transverse shear stress is going to be a maximum. Okay. Good. Okay. Yeah, so something weird happened in Canvas. I can't quite explain it. I think, well, you just taught me something. So in oh, I never fixed it. Well, this is weird. Oh no, it was right. It was fine. It was fine. Yeah, it's negative. Yeah, it was fine. Yeah, it was fine. It was fine. But I'm glad we checked. Okay, so did you have a question on number 2, Amir? I don't know if you have to just make it negative because it was fine, right? It was fine.
I don't want to put it in the first time. It didn't work.
It didn't? And it's negative?
Yeah. So you might have fixed something.
You might have fixed something. Okay. I don't know.
Finally works now though.
It does. Okay, good. But it is negative. No. let's go through that. Let's go through the actual problem and see what's the So let's draw out, right? So this one, because I was getting confused too. So you draw the element, right, such that it's at the top. Okay. And let's say that x is coming out, it's using that way, right? So just by looking at all the pictures, right, we know that we're going to have a shear stress from TF, okay, that's going to lie yank it in this direction, correct? Okay, so that is going to give us a, so that now we have to think, okay, that is,
Great pitch.
if I make an element, right, and x, right, right, and it's using it that way, and x is coming out this way.
You want
Then yeah, so then it is moving up, right? So this is how I see that TF is positive. That's fair. Right, because this is in the plane, this is on the positive x phase, and it's coming this way, right? Right, so it's moving up. So imagine transforming that over. So that's in the plane.
on the floor.
No, x direction is coming out. Like, z direction is this direction. No, because that has to be seen in the plane, right? So that's sitting in the plane. That's so take your drawing right here. The element, the way you got it right now, this element is in this direction, right? And we just said that it's going to the left. We just said tau at is going to the left. So that means left is this direction. It's up, not downward. It's up. Okay. Now the other one, all right, this shear stress is going to the opposite direction. The transfer shear stress is going the opposite direction, right? So that's going to be down. Is that good? Okay, good. Good stuff. Yes.
No good show.
I feel like I have two teams that call it thinking was like not never did.
This for caught up first. Here we go.
I'm always hoping he posts like full nights.
Yeah. Because all we have is intro of three stuff.
Yeah.
And YouTube videos.
I don't know where.
And then
Because we have some. But we need to know the rest of it. There's so many stuff. So, this on this that of the supply we have. I didn't know that. Yes. But I don't know that.
I'm gonna do the same thing on my done because I don't know why it's green from the light and I can't.
Oh, yeah, sure.
That's why I just left it on the table. Might be work. I think it should be max.
Question 3. Okay, we put for Q4.
I looked at the numbers and my head felt slightly
I don't know what to.
Questions?
Yeah.
Oh.
Oh.
Sure. So
Yeah, so
and then
we
this
do
question
both.
2 with organized,
Okay.
we just do additional moment.
So that's
The moment's in new direction.
I don't think the moment would apply for sheer stress,
It's your on the ZX, right?
but I don't think moment.
Yeah,
A moment would cause normal stress, not sheer stress.
that's true. So your PX, your P, and your M.
The only thing I thought from what I know that applies was PZ. From what I saw, was PZ and
And
TF.
T of yeah. So it's just question 3 again.
I don't think so. I didn't say so. They were absolute maximum. So
Ah.
we're going to be looking different. Probably never watched the videos. Good.
No, the big breakfast is simply not hard.
You got those shears. Shear.
Midterms?
No, just I gotta catch up on.
Yeah, I catch on. I need to catch up on physics 2B. Besides that, I should be fine. Yeah, I have the practice and midterms coming up because I just went last week.
I just one midterm season.
Cheers. It's going to be alright.
Yeah.
You don't have to say there's last midterm. I hope the air conditioning downstairs better than upstairs.
Joe, that's on. Joe, right.
You should have lost her.
Right dominated everything. Why? You do everything to right hand and right to right.
Yeah.
They're fake like
Okay, then
I
you
can't
use
write with my right.
once you have the single X and metallic Z, then you use move separation.
Yes. I do everything. Did I tell you about how my emails weren't sent over the weekend? I did my interview with Professor Sticfield. Just email questions, all this, everything. Send. Everything's like I'll send over the weekend. So I go to the interview. So I make my thought, the recent everything. And I'm waiting for
So the circulation in your fingers.
I'm not like fine, I just move these like
do this next week. Pretty sure. I just do want to start it for some reason. About some.
oh yeah. Okay, so
If you're press your arm against your back.
so you go from the left to the right. Okay, your internal bend moments and your internal shear should alright, and you're doing diagrams, the graphs. The thing to keep in
seems like it's I put a little bit. Two. Two electric space. Yes. Really? Yes.
But those are short answers to questions.
Those are equal, right? Just like that, exact same.
Like 40 pages.
But that based on that math, right? That's the nomenclature. You see it.
I don't know.
It's got to be way better than
Well, it's one way, so it's not so clear. That means 4.
Do you think Charlie would move the MATLAB to next week? Which one? Or like this week Monday? The MATLAB that's supposed to be week. Do you think he'll just make that this weekend? Since we're not having the exam.
We were not, we were allowed to just not do it.
good. Why not?
We still do it. In handwriting now after it was due. It was due and locked at 2 a.m.
Yeah.
We still do it.
If we lose points on that, like just gonna get it.
Good. Okay. That's fine. That's fine. That's good. That's what we're here for.
Yeah. He wants us to do at least 7. In the 8 ones option. And the 7 also option.
Yes.
Negative.
Negative.
Over.
No. Oh, okay. So, okay.
Nope.
Okay, what's up?
You have a note of the shear twist. I have this thing on email the shear. So,
Wait, so you have to take into account this as well?
yeah.
Down.
Yes, this one.
Yeah.
This way.
That.
This one goes that way.
Okay.
So it's shearing average.
Okay, so let's do which one you want to do first. Each circle is one. Each one. Right?
For a circuit.
Yes, exactly. So which one you want to do? Okay. Great. So,
Well, I would plan to do
I think I wrote it down somewhere.
is it tree and normal? No. It's okay.
this.
Oh,
Sure. Right.
So I have some exception for us.
T max. Sigma 1 on Sigma 2 over 2.
Minus
What?
Right.
Oh.
So that's not this one.
This is going to call P right across it. So right across, right? Okay. So, what's that? So shear is
Just T average.
so it doesn't care about the distance, right? There's a shear. So first, if you're thinking about it, P is causing the bending, right?
So sure, my own next thing is here.
Right. So if I'm putting a positive y element here again, then what's the neutral axis? What the neutral axis about which one it is positive, right? So like I can think of a y, right? So A is on the axis, right? Often when we think about bending, we think of like a point over here, here, as we know the neutral axis, or on the average. This location, for this situation, with P, the neutral axis is the line
And this is positive.
Yeah, I see that. That's fine. That's fine. I like those too. If you had told me I would appreciate it, doing that automatically, I would take that into account. We take a poll. Okay, so go down there. So go down. Black. Yeah. So let's go up. So up. So let's just look at this for a second. Okay, this is the thing between, right? So there's two areas. You see that the transverse shear stress is not at all. So that's what it's getting smaller. I don't know if you can tell the vectors are actually getting smaller as we get away from the neutral axis. Okay, and that's because this diagram doesn't even make it right. In this sense, the neutral axis is actually the long. And so this is the longitudinal axis, yeah. So the neutral axis is. I mean, where the stress is true. Yes. So the neutral axis, yes, can be going in and out of the page at the center there. Yes, but I think that the neutral axis is along the entire length. Yeah, it is. Yeah. Okay, so you see, it's maximum there. That's your maximum transfer shear, and then it gets to 0 at the top of the bottom of the beam. Okay, that's because if you look at the derivation, it's in the middle. Okay, so all of these bending stresses that are working against the transfer shear stresses now. And when at the top, there's no area, and there's no transfer shear stress. Okay, so that's that all. So let's get started.
What?
So one way is if I know I need one makes me rise. Okay, but that's tedious. So if you're interested in transverse shear stress, maximum transverse shear stress at the neutral axis, which is here, either ride those motional gyroforms. So now go down. So just here.
No. Why?
Oh, nice. Wait, yeah. Good.
So
Because I thought that was shear street used in part A.
now we go and change your turn. Okay, they won't work. But from our circular cross section, you can always use 4/3 tau lab. And what is tau lab? Tau lab is that P over the area minus the square. So that's the shortcut. So if you write down this one, it's actually the next slide. It's make it clear. I said, look, see the cross section, always use something else. And for a circular cross section, you always use 4/3 tau. So now that's the first part. So we've now got the first part here. So P, now let's we've got to draw a element. Okay, so first off, we have to say what is what is so remember X is moving out of the board and Z is moving to the left. Y is the shear force So that's the
You're
first
going to
one.
shoot us.
Now, let's look
I
at
was like
TI.
dripping sweat.
Here's the question.
See you, Sudhir. Have a good weekend.
You too, thanks.
See you all on Tuesday. So, TI is yeah, oh yeah, good, good, right. So TI is actually that direction. So at point A, which direction is shear stress? Because TI is such a cross shear stress. Which direction is yeah, yeah, yeah. So just draw it. No.
Hold on, I'm
Actually,
getting numbers.
it's the same direction. So, but it's a full, it's like a stress. Yes. Oh, thanks. Oh, there was that much, or is this all broken?
If I have to go through it.
Was it all broken? All right, thank you.
No problem.
Okay, so,
T is
that's
1,
stress.
Y is 13.
That like that. Just the line. Right. Now, what's the shear stress there? Because that's now a core, right? So that's going to be TC over J. So that's what we do. That's weird. Now, and that's a tau x c. C being the rate of yeah. So that's the positive c direction, right? C is to the left on the x face. So you can write tau x c.
We just
This
do direct
is just-
substitution.
Yeah, it's TC over J.
So it's basically it's easy to the other.
Right, you got a TC over J minus 4/3 T over A. That's correct. You use superposition. Right, superposition. Okay. And so now you've got, the question was asking for what is the shear stress, right? Right? So now you can calculate out tau x c. So the next question is, so let's say you have your tau x c, right? Next question is, what is, or is this structure will not fail according to the criteria of maximum normal stress? Okay. So what we want to do here
This is weird. This is torture if we don't put it down.
tau
We
x
keep
c
doing it.
to a
Okay.
normal stress. Okay, and what's interesting here is that element A is only experiencing shear. Okay? That means that element is a pure shear.
Because I
Right,
feel
so
like
if
taking
you're
on
on
a
a certain
17-inch laptop
pure shear
on a like a 3-inch by 3-inch like no, it's not happening.
Yeah, exactly. Exactly right.
Yes.
Okay. And the maximum
Yeah,
stress
that's what
is
I'm
right.
saying.
So you just draw on a more circular rate.
Because Mike's laptop is like
It's pure shear, right? So it's going to be down on the y-axis on the tau axis, right? Yeah. So it's just the point there. And opposite above that.
Oh, right.
Right, and now you draw the circle. Right, and that means that the maximum normal stress.
There we go.
Well,
Got it.
where's the yeah, exactly. That's right. That's it. So that's why you want to be late. That does
I did.
what we're saying is the ultimate shear. Oh, this is actually shear strength. Okay, so if this is shear strength, okay, then yeah, you can spread
Getting that.
both normal stresses.
All right.
But in reality, they're going to be, as long as this is larger than that, you're fine. Okay, I mean, you can convert them, right? They're both pure shear, right? This is a shear strength, right? This is so this will put it over to 200, right? That would be the maximum normal stress. Right? And yeah, so it's the conversion. No, you just add them, you just add them together and that's that. Right? Because
First question, yes. That's right. That's right.
Okay.
We do.
Oh. Yeah. No, that's fine.
Pull it, I dare you. Do it again.
Yeah.
Distribution.
I don't know what numbers we got, but it does.
Where? The bush. Yes. So. Oh yeah, it's this one, right? Yeah, this one. Oh, shoot, this is 0.03. Okay.
Vincent, they're
So,
leaving you.
There is sigma x, right? That's negative from MF. There's a sigma x that's positive from PX. There's a torsion from TF and there's a torsion from PZ. That's it. So you're going to have sigma x's and you're going to have tau x's. That makes sense? Okay. Good. Good, good. Woo! What a day, folks.